Genevieve speaking. This is a presentation about sampling distributions from simple random samples. We will specifically look at the sampling distribution of the mean. In the last presentation, we looked at how to select simple random samples from finite populations. For each random sample of a specific size n, we might compute a sample statistic of interest to us. Here, the sample mean x bar. If we draw many random samples and for each get a value for the sample mean, we end up with a list of sample mean values or a distribution. From this list or distribution, we could construct a frequency distribution or relative frequency distribution table or a relative frequency histogram like we've done before in chapter 2. This distribution of sample mean values x bar has itself a mean, so mean of x bar values, which we also call expected value of x bars. We can also compute a standard deviation for all these x bar values. And that's it. That's all there is to it. Sampling distributions are distributions of sample statistics. Statistics computed from random samples drawn from a population. And like with any other distribution, we can compute a mean and a standard deviation for those values. This relative frequency histogram specifically was constructed based on the mean values from 500 simple random samples of size 30 each. If we take many more samples, or if we increase the sample size, the sampling distribution of the sample mean can be approximated by a normal distribution, no matter which population we draw the samples from. This is a result of the central limit theorem. The sampling distribution of sample mean, x bar, can be approximated by a normal distribution as the sample size becomes large. Intuitively, this result does make sense. Each population, whichever one we draw our samples from, has a mean. By drawing a sample from that population, computing its mean to infer what the population mean is, sometimes we'll underestimate it, sometimes we'll overestimate it. But because we draw random samples from our population, we will rarely obtain values that are extremely underestimating or overestimating it. And because we draw a random sample from our population, we are most likely going to get values close to the true population parameter value. So we do have a normal distribution with few extreme values, a bulk of the values centered around its mean, and as many values likely to be below and above the mean. So if we draw samples and over again, each time computing the average of each sample, the average of all those averages will give us a good idea of what the population mean is. In other words, the expected value of the sample mean is the population mean. We say that x bar is an unbiased estimator of mu. And we just found this result to be intuitive. We can also easily prove it algebraically. You can find this proof in Appendix 7.1 of our text or in Genevieve's reading note. Also, when we average over samples of bigger size, get rid of those extreme values we might have gotten with smaller sample size. The variation in sample mean values decreases, or the standard deviation of the sample mean decreases, which means we'll have an even more distinctively bell-shaped distribution of our sample means, being even more likely to get a sample with a mean closer to the true population parameter values. Value. There's only one population parameter value. In other words, the sample mean is a consistent estimator of the population mean. From the algebraic expression of a standard deviation of the mean, we can easily see that it decreases as the sample size increases, which means that a large sample size tends to provide sample means closer to the population mean. And again, the derivation of the algebraic expression of the standard deviation of the mean is found in Appendix 7.1 or in Genevieve's reading notes. Note that to emphasize the difference between the standard deviation of the mean and the standard deviation of the population from which we draw the samples, we refer to the standard deviation of the mean as the standard error of the mean. Next, to get more intuition about the fact that the more samples you take, the better you're going to be able to zoom in on the population mean, or the bigger the size of one sample, the more likely you'll get a sample mean closer to the population mean. Let's consider farmer Denis or Denis problem. Denis is trying to figure out what the average weight of his straw bales is before he can sell them. There are many of them in his field. So he decides to take a sample of one straw bale. This bale here specifically is relatively heavy. You see how he's leaning on one side, let's say 50 pounds. If Denis relies on the average of that sample to estimate the average of the population, his estimate will be 50 pounds. Now let's say he decides to take another sample of size 1. So this bale is relatively light. You can see how he can easily lift it up really high. It's a 20 pounds bale. If Denis relies on the average of that sample to estimate the average of the population, his estimate will be 20 pounds. Now, what happens if he uses all the information he has available so far from both samples? Well, if he takes the average of the sample means, he will get a better estimate of the population mean, wouldn't he? There are, after all, both some relatively heavy and some relatively light bales in his field. So the weight of one relatively heavy one in the first sample, or the weight of one relatively light one in the second sample, is not as good as the average of the averages of the two samples to best represent the average weight of all the bales in the field. We started with one sample of size 1, and then we drew another sample of size 1. Now, instead of drawing another sample of size 1, let's increase our sample size to 2. This second bale, we remember, is relatively light. Denis can easily lift it up. 20 pounds, we said. If Denis relies on the average of that sample to estimate the average of the population, his estimate will be 35 pounds. 50 plus 20 divided by 2, that's 35. So by increasing his sample size from 1 to 2, Denis is able to get a better estimate of the average weight of the straw bales for the whole field. There are, after all, both some relatively heavy and some relatively light bales in his field. So the weight of one relatively heavy one in the sample of size 1 is not as good as the average weight of the sample of size 2, where we have one relatively heavy bale and one relatively light bale, to best represent the average weight of all the bales in his field. In other words, increasing the size of our sample allowed us to average out the more extreme values in our sample. The variability in the values of the sample means decreases as the sample size increases. This is why increasing the sample size gets us sample means closer to the population mean. Still, for a given sample size, here size 2 again, one specific sample might not give us as good an estimate of the population average as another. We have to keep that in mind, and we will use the sampling distribution of the sample mean to assess our level of confidence in using one sample mean to infer what the corresponding population mean is. One more thing before we go to the last section of this presentation. Note that with our Denis Farmer example, to simplify things, we didn't use simple random sampling, but instead convenience sampling, where we identified our sample by convenience as opposed to selecting samples based on each sample having the same probability of being selected as we did in this simple random sampling case. So the last thing we want to do is look at our result of from a simple Excel simulation to further demonstrate that the sampling distribution of X bar can be approximated by a normal distribution as the sample size becomes large, no matter what the distribution of the population we draw the samples from is. We draw our samples from the following uniform distribution. We looked at uniform distributions in chapter 6. Here we modify the text example in section 6.1 slightly, and we plotted f of x values for x values ranging from 100 to 300. The difference between this graph of the uniform probability distribution and the one found in your text is those vertical lines that are added to close the surface area under the graph of our function. We use the rand between function introduced in the last presentation to draw samples from that uniform probability distribution. Here's how our worksheet is organized. For those samples of size n equal to x1 is our first value and x2 is our second value in each sample. For each sample, we compute the average x bar of those two values, and we also keep track of how many samples we have under the column labeled sample. So here we have sample 1 through sample 10, and we can easily increase the sample size or the number of samples. And next we construct histograms of the means from these samples, just like we did in chapter 2. Here's an example of what we got. The first row of histograms is from samples of size 2, with more and more samples being drawn, at first 10, then 100, and next 1000. The middle row of histograms is from samples of size 5, with from left to right the same increase in the number of samples, 10, 100, and 1000. Finally, the last row looks at histograms constructed from samples of size 30. If we look at this across columns instead, the first column looks at the same number of samples drawn, 10, and from top to bottom increases the sample size from n equal 2, next n equal 5 to n equal 30. Same for 100 samples and for 1000. Looking at our sampling distribution changes as we increase the sample size. With 100 samples histograms, we see that as the sample size increases, we're getting sample mean values more and more likely to be closer to the population mean. And looking at how our sampling distribution changes as we increase the number of samples with the sample size set at n equal 5, we see that as the number of samples increases, it looks more and more like a normal distribution. So these simulations confirm our intuition. And this concludes our presentation on sampling distributions of sample mean.